In the last video, and probably in the in-class activities as well, you probably noticed that it was a bit clunky using the definition of limits for functions. So what we're going to try to do in this video is make that a little bit easier by finding a connection between limits of functions and convergence of sequences. So we're first going to translate the idea of x approaching a given number into a precise statement about sequences. We're going to prove a theorem that reduces computing limits of functions to finding limits of sequences. And then we'll show an example about how you can apply the theorem and use some of the theory that we developed with sequences, making our proofs a little bit easier for limits. So remember back in the old days, one of the ways we would visualize the limit of f of x as x approaches a of L is by imagining what happens as x gets close to a, and then at the same time imagine what happens as f of x getting close to L. So if we think of getting close to a as approaching a in discrete steps, well, that's exactly what a sequence is. In fact, it's a sequence converging to a. So the question we ask is, can we describe the limit as x approaches a of f of x equals L as having some sequence xn converging to a while f of xn converges to L? And the answer is actually pretty close, not too far away. So first of all, there are lots of sequences that converge to a. And one of the things we want to avoid is we don't want any of the terms in the sequence to equal a, because part of our definition of a limit is that our x value cannot equal the number that x is approaching. So here's a little bit more precise conjecture of what we hope to have happen. So suppose we have a function from an interval I to the real numbers. We believe that the limit of f of x as x approaches a equals L if and only if, whenever we have a sequence xn that is in the interval but not equal to a, that converges to a, then we have that f of xn converges to L. And in fact, that is exactly the theorem that we're going to get. And we're going to prove it in two parts. It's an if and only if, so I'm going to prove each direction separately just so we can keep things a little bit more manageable. So for the first theorem, or the theorem part 1, we're going to assume that the limit of f of x as x approaches a is equal to L. And we're going to prove that if xn is a sequence in the interval but not equal to a that converges to a, then f of xn converges to L. So we're going to let epsilon be greater than 0, and we're going to find our big N, a natural number, such that whenever little n is bigger than big N, we have f of xn minus L, or at least the absolute value of that, less than epsilon. So let's apply the definition of what it means for the limit of f of x as x approaches a to equal L. That means there exists some delta greater than 0, such that anytime you have the absolute value of x minus a bigger than 0, so x is not equal to a, but less than delta, you have that the absolute value of f of x minus L is less than epsilon. So we know that xn converges to a. That means there exists some natural number such that whenever you get past that natural number, whenever little n is bigger than big N, we have absolute value of xn minus a is less than delta. Remember, delta isn't given the name of epsilon, but it is a positive number. So that means that eventually our xn's n minus a's are going to be, the absolute value is going to be less than delta. And also note that xn is not equal to a, so for all of those terms past big N, we have the absolute value of xn minus a bigger than 0, less than delta. But whenever that happens, we have, for all little n bigger than big N, since absolute value of xn minus a is bigger than 0 and less than delta, that means that the absolute value of f of xn minus L is less than epsilon. And that means that f of xn converges to L, which is exactly what we wanted to prove. All right, so the first part of that theorem was actually not too bad. The second part is going to take a little more doing, though. It's a little bit more involved. So let's go ahead and state the theorem. We're going to assume that every time we have a sequence xn that is in the interval I, but not equal to a, but that converges to a, we have f of xn converges to L. And then we're going to prove that the limit of f of x as x approaches a is actually equal to L. And proving that one directly, it turns out, is not so fun. So we're going to try the contrapositive, which is, well, maybe not so fun either, but it's a little bit more fun, right? It's a little bit more doable. So the contrapositive says we're going to assume that the limit of f of x as x approaches a is not equal to L. And then we're going to show that the if part of the theorem is false, right? So what does that mean? That means there exists a sequence xn in the interval, but not equal, none of the terms equal to a, that converges to a, but f of xn does not converge to L, right? It's an if-then statement. That means the if part is true and the then part is false. All right, so that's what we're looking for. But here's the big issue. What the heck does it mean for the limit of f of x as x approaches a not equal L? What is that supposed to mean, right? Well, let's go back to what it means for the limit to equal L. So the limit of f of x as x approaches a equals L. We have a nice little definition for that. That is, for all epsilon greater than 0, there exists delta greater than 0, such that for all x, if 0 is less than the absolute value of x minus a, which is less than delta, then absolute value of f of x minus L is less than epsilon. So that's what it means for the limit to be equal to L. What does it mean for it not to equal L? Well, it's just the negation of that, right? You remember back in Math 210 how fun it was to negate quantified statements. Here we have a triply nested quantified statement. We have two for alls and a there exists, and they're all living inside one another. So that is going to be a little bit of a challenge, but we can handle it, right? Again, this is just a little bit of advanced Math 210 back when we were doing quantified statements. All right, so here's what the limit means, right? The limit equaling L means for all epsilon greater than 0, there exists delta greater than 0, such that for all x, if 0 is less than the absolute value of x minus a, which is less than delta, then absolute value of f of x minus L less than epsilon. So we're going to take this one step at a time. Now remember, when we have a for all and we negate it, it becomes a there exists. And when we have a there exists and negate that, it becomes a for all. So that's going to make this thing go a little bit more smoothly, because we start off with for all epsilon greater than 0, which means for the negation of that, we're going to start off with there exists epsilon greater than 0, such that, right? Now, up in the original statement, we have there exists delta greater than 0. When we negate that, we're going to get such that for all delta greater than 0. And then such that for all x in the original statement, that for all x is going to become there exists x with, well, now we're left with an if-then statement. And with an if-then statement, when we negate that, the if part is true and the then part is negated. So we're going to have 0 less than absolute value of x minus a less than delta. That we're keeping, right? That's our if part. That is going to be kept the same. And then the then part we're going to negate. So instead of absolute value of f of x minus L less than epsilon, we're going to have absolute value of f of x minus L is greater than or equal to epsilon. So that is what it means for the limit not to equal L. And that is what we're assuming in the contrapositive of the theorem that we're trying to prove. All right, so this is just, again, what we had before. This is what we're assuming. And now what we want to do is find a sequence that where the sequence converges to A but is never in A, but the f of xn does not converge to L. So again, we're going to let epsilon be as in the definition of the limit not equaling L. So there exists epsilon greater than 0 such that all this other stuff. There exists that epsilon, that's the epsilon we're talking about. The one that exists that makes all the other stuff after that true. And again, there exists means there's just one, but we just need one, it turns out, for this theorem. So we're going to apply the statement above where delta is equal to 1 over n, because it's saying that for all delta greater than 0, some stuff happens, right? That could be any number greater than 0, and we're going to use 1 over n because, of course, 1 over n is greater than 0. So that's a perfectly good delta that we can use. So for all delta greater than 0, including 1 over n, that means there exists some, we'll call it xn because it's associated with 1 over n, such that the absolute value of xn minus a is bigger than 0, so xn is not equal to a, it's less than 1 over n. And absolute value of f of xn minus l is greater than or equal to epsilon. So the nice thing about these xn's is there's an x1, an x2, an x3, an x4. They form a sequence. And not only that, we have 0 is less than the absolute value of xn minus a. That means none of the terms in that sequence are equal to a. So this sequence is looking pretty good, right? This is starting to look like the sequence that we want. We have a sequence of terms that are in the interval I, but not equal to a. Right? That's what we have right now. So we also have that absolute value of xn minus a is less than 1 over n. If we turn that into a non-absolute value set of inequalities, that means negative 1 over n is less than xn minus a is less than 1 over n. We can add a to both sides to get negative 1 over n plus a is less than xn is less than 1 over n plus a. We might notice that both negative 1 plus a, negative 1 over n plus a and 1 over n plus a, they both converge to a. And since xn is right in between those, that means xn converges to a, which is exactly what we were looking for. Remember, in the previous slide, we showed that all the terms of xn were in the interval I, but not equal to a. And now we have that sequence converges to a. All we have to show now is that f of xn does not converge to L. We're doing great. Right? So we applied the squeeze theorem to show that xn converges to a. All right, so we have that f of xn, the absolute value of f of xn minus L is greater than or equal to epsilon. That means those f of xn's never get within epsilon of each other, right? That implies that f of xn does not converge to L, and that is exactly what we were trying to prove. All right, so that's kind of how the proof is going to go. Let's see if we can go set it up in a line so it's a nice logical argument. So we're going to prove that we're assuming that every sequence xn and we're going to prove that whenever that we have xn and I minus a that converges to a, we have that f of xn converges to L. Then we can conclude that the limit of f of x as x approaches a equals L, and we're going to prove that by the contrapositive, which means we're assuming that the limit is not equal to L, and we're going to prove that there is a sequence xn in the domain but not equal to a that converges to a such that f of xn does not converge to L. And basically all that work we did in the previous slides, we're going to be putting that in, just organizing that work. So we know the limit is not equal to L. That means there exists an epsilon greater than 0, such that for every delta greater than 0, there exists x with 0 less than the absolute value of x minus a, and the absolute value of x minus a less than delta, and absolute value of f of x minus L greater than epsilon. Thus, for each natural number n, since 1 over n is greater than 0, there exists xn such that absolute value of xn minus a is bigger than 0, so xn is not equal to a, but is less than 1 over n, and absolute value of f of xn minus L greater than or equal to epsilon. So we know absolute value of xn minus a is not 0, so xn cannot be equal to a. That means that the sequence xn, the terms are all in I minus a. But since the absolute value of xn minus a is less than 1 over n, our work in the previous slides, along with all that squeeze theorem stuff, imply that xn converges to a. However, since the absolute value of f of xn minus L is greater than or equal to epsilon for all n, it cannot be true that f of xn converges to L, which completes our proof because we found a sequence in I minus a that converges to a, but f of xn does not converge to L. All right, so an example of how we can actually use this theorem to solve some other theorems about limits without too much work. Suppose we have f of x, the limit as x approaches a equal to L, and suppose c is a real number. Then we're going to show that the limit of c times f of x as x approaches a is equal to CL. Something that is very intuitive, but if we had to use the definition, might be a little clunky. But turns out using sequences is going to make it a lot easier. So by what we previously proved, we can prove this by assuming that xn is a sequence where each xn is not equal to a, and proving that c times f of xn converges to CL. Right? So we're going to apply that same theorem actually to limit of f of x as x approaches a equals L. We know that limit is equal to L, which means that since xn converges to a, we know that f of xn will converge to L. But remember, we previously proved that whenever an converges to a number L, any an converges to a number L, then can converges to CL. That was one of the theorems that we got when we were studying the theory of sequences. Applying this to an equal f of xn, we get that c times f of xn converges to CL, which is exactly what we wanted to prove. All right, so now I think you're ready to work on the in-class activities, limits and sequences. Just go ahead and click on the link below this video.